To our video here on the Lagrange error bound. So what we're going to be talking about here is we kind of sort of touched on the previous video a little bit, but not really. It's just really talking about the error that we have for the remainder of a function here. So we're going to be using the Lagrange error bound. Let's go ahead and read through this real quick for what's important here. So power series in x, the partial sum's the first few terms. The tail is the rest of the terms. The remainder is a number you get by adding all of the terms in the tail. Okay, so that's what that means. So just for terms of vocab here. So if you take the partial sum plus the remainder, then the error is the error you make by assuming that the f of x is the partial sum. So if we find just a partial sum, like, oh yeah, that's good enough for me, because if you take a partial sum, you can get a pretty close approximate to what the actual sum is. So the error is the same number known as the remainder. So we're taking that the error is going to be the remainder. So the error bound is the number known to be greater than the absolute value of the remainder. Okay. So what this really means is r sub n, which is the remainder, is going to be the sum of the series, the actual sum minus the the terms that are used, so the partial sum, and that is bounded by r sub n, okay, n to infinity of f of x dx. So that's what that means. Okay, and this is kind of what we're going to be doing here, notation at least for some of these problems. You can read that one on your own. So again, so the Taylor's theorem, we touched on this a little bit. If the function is differentiable through order n plus 1, so beyond the next term, in the interval containing c, then for each x in the interval there exists the number z coming out of nowhere, between x and c such that, and then here we go. So you get the partial sum up to whatever number terms you do, plus there is the remainder, where this remainder is equal to this right here. All right. And then z is the place where the max is. And that's what confuses a lot of people right there. So z is going to be where the maximum value is. Okay. Notation. I want to talk about notation. Yeah, so talk about notation a little bit with what we've done so far previously to new notation. So what we've done before was we've done the polynomial, right, just with some type of, I'm just picking numbers right here, minus the actual function right here. So the polynomial using 4 terms minus the actual function is going to be less than 1 over 3,000. Like, we've done a problem like this in ours before. So let's just say that this is our notation. All right, so here's the error. Just picking some numbers here. So here's our error just of this. So our error can be less than 1 over 3,000. We've done that with an alternating series with a stop and chop. Okay, so similar to that. So now we're going to get this little slightly different notation here. So let's just say that I have this 1/4 minus f of 1/4, which is the error. Okay, this is going to be less than or equal to write this down first, and then I'll explain it. X to the 5th of x. All right, so kind of what I'm doing here is I'm using this notation now. Okay, so n in this case would be 4, so 5 factorial is the next one. So it's the next derivative, so it's the 5th derivative. And this little part right here represents the maximum value. So easiest thing to do here is just to hit up some problems. Okay. Function f has derivatives of all orders for all real numbers x. Assume that we have f of 2 is 6, f prime of 2 is 4, f double prime of 2 is negative 7, f triple prime up to is 8. Right, third degree polynomial for f about 2, and then use it to approximate 2.3 to 3 decimal places. Okay, so this is a problem that we've done before. So we're going to go ahead and use this little tidbit of information here. Just as a reminder, we should have this memorized though. But we're going to be able to do that. It's going to be 6 plus 4, and we're centered at 2, so x minus 2, minus, the next derivative is 7, so it's a minus because it's 7 over 2 factorial, that's x minus 2 squared, is plus or minus, is going to be a plus. The next one is 8 over 3 factorial, x minus 2 to the third. Okay, so this is approximation of our Taylor polynomial. Okay, up to 4 terms. And then let's go ahead and estimate what f of 2.3 is. So all you can do is just type this in your calculator. Not a big deal. Type that in your calculator. Get an answer of 6.921. That one, not new. Coming up, a little bit new. The fourth derivative of f satisfies the inequality where it's going to be less than or equal to 9. Okay, in this closed interval from 2 to 2.3. Use this information to find the bound and the error for your approximation. Okay, so this right here means that we are, this is a fourth derivative, by the way. So this is the bound for the fourth derivative. And this is our maximum value right there. So my remainder of this polynomial is equal to pretty much this guy right up here. I'll just rewrite it down for you. N plus 1 of z x minus c, which is the center, n plus 1. So again, we're going to the next term here. So since so this is the formula. So now I have the third one, right? So I'm looking at the next number, which is going to be 4, and you'll see the 4s pop up here. So this is going to be the fourth derivative. Put a little 4 there. Fourth derivative of this z value, x minus 2 to the fourth, all over 4 factorial. And that is less than or equal to the greatest number. What's the greatest number here? Well, it says it was 9, so it's 9. So this is just going to turn into 9. So really not too bad, okay? Trying to make it as least confusing as I possibly can. X minus 2 to the fourth, all over 4 factorial. Okay? So now plug in here my 2.3. So if I go ahead and plug in a 2.3 into x for here, just pretend I do it, I'm going to get 0.003. So this is the bound for error. Okay, so that's what this is asking, just to find r sub 3 of 2.3, which I did. Use your answers in A and B to find an interval. So pretty much now we're just trying to find the interval. Okay, so all I'm going to do here is I'm going to take this value right here, and I'm going to take away 0.3. So I'm going to take this f of 2.3. I'm going to subtract my 0.003. It's going to be in between the f of 2.3, which is going to be the f of 2.3 plus my bound. So I'm just adding and subtracting this bound on both sides. So this is going to turn into, do some real quick math in my head here, 918. And this is going to be 6.2924. Okay. So could the actual value actually equal 6.922? Yes, it's in the interval. Could it equal 6.927? No, because it is not in the interval. So that's one of these really, really scary problems all set up for you. Okay, so it's really not too bad for error bound. Just got to memorize this, and this again gives us our bound. Okay, and we just take that bound and we're going to add and subtract it from our approximation here up to whatever random terms that we have, and then that's what the actual value could be. All right, so let f be a function given by this right here, and let p be the third degree polynomial about x equals 0. So let's go ahead and find p of x. So what you have to do here is you have to find, so it's centered at 0, so you need to find f of 0. If I plug in a 0 here, I'm going to get root 3 over 2. Find f prime of x, and then we'll plug in a 0 there. So it's going to be, derivative of the inside is 5. It's going to be cosine 5x plus pi over 3. So f prime of 0 is going to equal 5 halves. So you plug in a 0, you're going to get cosine of pi over 3, which is just 1/2 times 5. And you get the idea from there. How many am I doing here? 3? Okay, that's not too bad. So this is going to give me negative 25 sine of this 5x plus pi over 3. So f double prime of 0 is going to give me negative 25. Yeah, I'm looking at my key and my key was wrong. Okay, negative 25 root 3 over 2. I didn't leave my key. And we do this, we're going to get negative 125 cosine of 5x plus pi over 3. Plug in a 0, and I'm going to get negative 125 over 2. Okay, so my polynomial of power 3 is going to be root 3 over 2. Okay. Again, you can use this formula if you don't know what it is. It's centered at 0, so I don't need the c value is 0, which is super nice. This is going to be plus 5 over 2x minus, because it's I'm going to get 25 root 3 all over 2 times 2 factorial x squared minus 125 over 2 times 3 factorial x cubed. There we go. All right, so there's a polynomial. This one just comes right out and says it lets you Lagrange error bound to show that this has to be less than 1 over 1200 here, okay, at 1/15. So let's go ahead and find our value here. So remainder, the error bound here is going to be the fourth derivative at z x to the fourth all over 4 factorial. Okay, because c is 0. I'm looking at everything for the next. So we know that this is equal to, well, the absolute value of this at least. Just put these around here. Absolute value, because we're looking for error bound. It should be absolute value because I don't want negatives. Is going to be equal to f of 1 over 15 minus p of 1 over 15. All right, which is less than or equal to, so let's plug everything in. So what's the maximum value we can have here? So if we go to the fourth derivative, I'm going to get 625 sine of 5x plus pi over 3. Okay, so the maximum value of this can be, is going to be 625. I'll show you real quick. Helps if you're familiar with trig. The reason is, I'll show it over here. So negative 1. So sine, no matter what the sine function is, it's in between. It's between negative 1 and 1. Right? So now if I just multiply it by 625, that function sine, I wrote this through. I can't write things down. It should be 625. It's going to be in between negative 625 and 625. So the maximum value here is going to be 625. That is going to be 625. X to the fourth, this is going to be 1/15 to the fourth all over 4 factorial. All right, so what does that tell me here? Can I use am I allowed to use a calculator here? I don't know if I'm allowed to. I'm going to pretend I don't know how to. Okay, so I'm going to rewrite this because I'm not too sure if I'm allowed to use calculator on this one or not. My notes don't have a calculator, so I'm just going to not use one. So 625 can be written as 5 to the fourth times, I can break this down as 1/3 times 5 to the fourth all over 4 factorial. So when I do that, 5 to the fourths are going to cancel out, and then I'm going to be actually left with 1/4 factorial times 3 to the fourth, which is going to be 24 times 81, which I do know that that is indeed less than 1/1200. So I can say that this is 1/81 times 24, which is less than 1200. So following this string right here, I just use the Lagrange error bound to show that this has to be less than 1/1200. All right, that's going to wrap it up.